Hi everyone, welcome back to the channel. In today's video, we will discuss how to design cross-coupled voltage controlled oscillators or VCOs. And this is a nice place to do that because in the past we've already talked about cross-coupled oscillators in terms of theory and also some other design aspects. And we also discussed MOS Varactors, right? So the reason I did these is because I wanted to talk about VCOs. So let's get into that. I will be using the designs that I covered in this video, and this video. So if you haven't watched them, you can go to the tape out series and watch those beforehand, since we'll build on those. Okay, so let's move on to the notepad and we'll quickly look at some design equations, what we're looking for, and then we'll come back to Cadence and then design it in Cadence. Okay, so we'll call this the cross-coupled controlled oscillator. Okay. It's a very popular oscillator that many people use, especially at higher frequencies. So it's important to kind of know how to design it. So if you remember, we said in the previous video, we'll just do a quick recap that have a tank. And this was for the cross-coupled oscillator. So these cross-coupled pair here. And then you have the current source on the bottom, right? So connected like this. Okay. And we had some design equations for it. We said we had, if you have a DC power consumption limit of about 1 milliwatt, then the current is around 1 milliamp when you have 1 volt supply. That was the peak current. And then we said from that you have some design equations. So the amount of resistance you need for a given swing is, because you don't want to exceed, you don't want to move these transistors into triodes. So we showed that the resistance you can get the amount of resistance from that. And that's around 455 ohms. And then we also said that based on the Q, then you can get the inductance, which is RP over QL omega naught. And that was around 905 picohenry. And obviously from the resonant frequency, you can get the capacitance, omega naught square times L, which was around 280 femtofarad. And this actually came down to 270 femtofarad because there was 10 femto from the parasitics. And lastly, we set a W over L ratio to get enough GM to be around 5 micrometers. 5 to 1, right? So 5 micron by 1 micron. Okay, so this is kind of where we'll start. But to ensure that we can tune the oscillation frequency, which is very important for many, many designs, I'm not going to go into the applications, but if you know that, and a voltage control oscillator is actually much more useful than just any oscillator, right? So to control the voltage, essentially we want to control the oscillation frequency. What we need to do is we need to control this parameter. So which obviously means that you need to control either this or this. And typically it's much easier to control the capacitance using a varactor. It's very hard to control the inductance on chip. So that's what we'll do, is we'll use MOS varactors, which I covered in the last video, to change this capacitance. Okay, so what does that actually look like? So we will connect pair of varactors here, which I'm going to draw like this. Right? And this will give us the fine tuning. right? But you also want coarse tuning in some applications, so we'll also discuss that today. So for that, we'll add a capacitor bank. The switch like that. So that's one. We'll add a bunch of them to give us a wide variety of tuning voltages. Okay, so this is for discrete tuning. Okay, all right. We also saw that in this case, at 10 gigahertz and 1 milliwatt, the phase noise figure of merit was approximately 185 dB. That's really good. I would say that's pretty good design. Today, what we will try to do is that we'll try to get close to this, maybe around 175 or so. That's not really state of the art, I would say, but it's still just a good design. Of course, to really improve the phase noise beyond that, you need to also change some of this topology of the circuit here. We'll explore the phase noise of VCOs in another video. So today I won't focus too much on phase noise, although we will kind of, not try to destroy the phase noise and still have a reasonable value for it. Okay, so around 175 maybe for the form. So around 1 megahertz offset does corresponds to around minus 100 dBc per hertz, and we'll try to hit that number. Okay, so I'll say at 1 megahertz offset, we want around minus 100 dBc per hertz. And we'll see how close we can get to this. This is a good number. It's not great, it's not state of the art, but it's still good. Okay, so let's get started with the design. So let's set some parameters, right? So the first thing is, what's the frequency range? So including discrete tuning, let's try to go from maybe 9 gigahertz to 11 gigahertz. That's 20%, right? Yeah, that's a pretty good number to hit. The reason I'm using the 10 gigahertz band is that later on we'll discuss doubler chain and try to get to 77 to 84 gigahertz. That's like the automotive radar band, and that's just as an example. But of course, you can use the same concepts at different bands. Okay, so that's what we're trying to hit. So that means at PU's L of around 905 picohenry, right? We need the capacitance. The lower value should be 1 over 2 pi 11 gigahertz times 905 pico, and that comes up to around 231.5 femtofarad. Right? And then the high value of the capacitance to hit this band is 1 over 2 pi times 9 gigahertz times 905 pico, and that's approximately 345.9 femtofarad. Okay, so this is the range that we're going to try and hit. Okay. All right. So delta C, which is the total capacitance range that we need, is C high minus C low. C low. And this is about 114.4 femtofarad, right? Okay, so the next question is, how many levels do we want? Like, how many discrete levels do you want? And that depends on what the slope of the fine-tuning capacitance is. So we'll discuss the slope of the fine-tuning capacitor in more close detail when we discuss PLLs. So it has to do with the KVCO of the varactor. But in this case, let's just say we want to divide this into 8 different voltages, right? Which means that's a 3-bit discrete tuning. So if it's 3 bits, that means the CLSB, which is the step size for each discrete tuning, should be approximately delta C over N, where N is 8. So that's around 14.3 femtofarad, right? So it's an important number to keep in mind. Okay. Okay. Then the next is the delta C, which is the fine tuning. How much do we want to tune the fine tuning knob? And we want it to be around 1.5 CLSB. I'll explain why that is. So this is again a heuristic kind of value. You can be a little bit more precise in exactly designing this, but for now I'm just doing it sort of this heuristic approach. Right? So 21.45 femtofarad. So what does this really mean, right? So if you look at, let's say, capacitance versus voltage for our capacitor bank plus the varactors, then your voltage is V, let's say, capacitance is C. Essentially what you have is you will have tuning that looks something like this. That's too close. And goes up. So this is your 0, 0, 0. This is 0, 0, 1, and so on. And this is your 1, 1, 1. When all the caps are on. Actually, when all the caps are off. That's when you get and all the caps are on, you get the highest capacitance. Okay, so in this figure, what is CLSB and what is delta C? So this value is C low, right? And this value is C high, right? Okay, then this is CLSB, and if I take this down here, this is delta C, right? So the reason I chose delta C to be 1.5 times CLSB is that I want there to be some amount of overlap here, right, between the two discrete tunings so that you can smoothly switch between one to the other. If you don't do that, because of process variations, sometimes you may get a gap between the lowest value of the second state and the highest value of the first state. If you have a gap there, then there are certain frequencies you cannot reach, right? So that's why 1.5 is kind of a decent number where you have enough overlap so that even with process variations and so on and so forth, you will still have some overlap between the two states. Okay, so hopefully that's clear. All right. So of course, this is for each capacitance. If you put them in series, as we'll see that they are in fact in series, then the C LSB series is half of this, right? So that's approximately 7.15 femtofarad. And delta C series is approximately 10.725 femtofarad. These are the numbers that we'll start with. Of course, this is just kind of a rough hand calculation, back of the envelope calculation. When we go into the simulation, we'll see that we need to modify them a little bit here and there. Okay. So, okay, so these are the numbers we're going to try and hit. So let's jump into Cadence and we'll design our first the varactor and see what kind of delta C we're able to achieve. And then we'll come back and then we'll look at how to design the capacitor bank. And then again, go ahead and go to Cadence, design the cap bank and continue from there. Okay, so let's jump into Cadence and see what to do next. Okay, so if you remember, this is the design that we had last time where we designed our oscillator. So I'll just make a copy of this. So let me call this 807. Right. So the first thing is we want to make our varactors and then test it. So this is the test bench we used for the earlier varactor video. We'll modify it a little bit so that we can do it for two back-to-back varactors. So let me actually delete this. We'll put our thing there. And GPTK actually has varactors, mouse caps. So although in the last video I basically built mouse caps using the transistor models, you can directly use this or you can also use those. The one thing you need to be careful when you're using those is that in some of the cases I said you can bias the body to negative values. When you do that, you have to be very careful because the body is shared between many transistors. So if each transistor has its own body, for example, if it has like a P well and a depend well, where you can separately bias the P well and depend well so that the bodies are separate, then you can have a negative voltage for your MOS varactors. If not, just connect the drain, source, and bulk together, and then just use the strong inversion region or the accumulation region, depending on what kind of model you have. Okay, so in this case, we will go ahead and use the NMOS cap. So let's place one will be here. Okay, you can bias one there. Need the VDD. Put one VDD here. And we also need inductors. So I'm placing these inductors so that the bias voltage is the same as what we will have when we have our um, actual oscillator, right? Because the oscillator biased at VDD lines. Yeah, ground. The other thing I want to use is go to GPDK. We will actually also use a MIM cap because we want to provide separate bias. Let me actually put this in and I'll explain what I'm trying to do. Okay, so the reason I have it like this is that I want to be able to bias this from 0 to 1 volt. Now, since you have VDD here and this should be 1 volt, call this V mask cap, right? Okay, so since this line is at 1 volt right now, then I have to bias this higher than 1 volt, right? And that body is probably going to be connected to 1 volt, which is not a good thing. So you want to keep this at ground, DC, and that's why we have these big resistors. Since these resistors obviously don't draw any DC current because both sides they are caps, so it would bias this node at DC, and it's large enough that for AC it looks like an open circuit. And that's basically the idea. Okay, we need to be careful in the way we bias these guys. So, or size these guys. So I'll call this Um, so this is the min cap and the mom cap. No, min cap, yeah. Min cap, and that's the width. It's the varactor, min cap, number of fingers. And then for these guys, we have varactor mask cap, width, and varactor mask cap, number of fingers. These resistances can be large, so I'll make it maybe 5K. Let's keep it at 1K. Okay, and these can be large. Don't make this 1 micro. I'm just trying to create an open circuit here. You shouldn't make it more than 1 micro, otherwise it can cause convergence problems, but 1 micro should be fine. Okay, so that's that. Gives this big equation, but that's not a problem. So now what we'll do is we are going to load our Varactor test bench that we had earlier. I can close this. Let's save that. And then we want to set some values here. So let's say 445 milli, that doesn't really matter. And for the Varactor MIM and MOS, okay, I think MIM cap should be large, so maybe we'll say 50 and 1 micro, 25 and 1 micro. Okay, so let's see what we get with this. Oh, I also need to change this to V cap, and we'll go from 0 to 1. I also want to specify number of points, 51. Okay. Guess there is some error. Oh, no error. Okay. So you can see that right now, at least it's going from around 25 femto all the way up to 27 femto. So it's not changing much, right? And the reason behind that is that the sizing of the mass and min cap is not correct. So let me actually fix that. Okay, so we'll change the length to 5 microns for the min cap, and let's go in here. Let's make this 10, make this 5 microns. Let's make this 2 microns and this one 50. So essentially I made the mask cap bigger just so that we get a larger uh, capacitance tuning range, right? Okay, so with this it looks a little bit better. So we have about, say, from 32 femto to maybe around 45 femto. So you don't want to use all of it. You kind of want to use only the linear range. So the way you can check that is we send this to calculator and we'll take a derivative of it. So if you plot the derivative, then you can see that maybe the peak is around 40 femto. You don't want to go below 15 or 20, right? So we'll maybe say from 325 to 800. That seems reasonable. So let's actually do that. 0.325, date, and then let's plot the capacitance again. Okay, so this is not completely linear, but at least it's not too bad, right? So this looks like a good range. So now we can see that we can also do one more thing to get the delta capacitance. I max of this minus y min of capacitance. So yeah, that gives us what we need. Send that to calculator. And then here we can change this and we can call this delta cap. Okay, So that gives us essentially what the delta capacitance value is. It's around 12.4 femto, right? Okay, so let's go back to the notes and see we'll next discuss maybe how to design the discrete tuning. And we said that, okay, 12.4 femto is good enough, right? So let's go back to the notes and take a look at what we had. Okay, so from simulation, we have delta C series combination was around 12.4 femtofarad, right? Okay, so that's actually good. We'll see actually later that we need to increase it maybe a little bit more. Although in simulation we saw calculation we saw that it needs to be only around 10.7. Because of other parasitics, we may need to increase it more, and we'll see that. All right. So the next thing to do is to discuss how to make the cap bank, right? Because we want to get this value now, the LSB value. Okay, so let's maybe do it on a new page. So cap bank, right? So how do you make this? So what we're going after is something that looks like this, right? You have two capacitances and a switch. Right, so how do you actually make that? The simplest way to do that is to just use a transistor for the switch, obviously. So let me actually draw it a little bit below. Okay, so we have your transistor there, and that's your capacitors. These two capacitors can be MIM caps, for example. Okay, so the problem is that if you implement it directly like this node and this node don't have a well-defined voltage, right? So you can't just apply a voltage here and then expect this to behave like a switch. So in order to kind of define this voltage correctly, we need to use an inverter. So we will do it this way. It's a bad inverter. We have an inverter, and that connects with a resistor like that. Let me actually do this in a different color. Okay, so we have inverter and resistor that way. And we also need to use the input of the inverter. Come on. To connect to these two nodes. Okay, so what happens now, right? So if I have a 1 here, which is a high, then this is 0, which means that the drain and source are high and the gate is 0, right? Which means it's a completely off switch. In the other case, if you have a 0, let me use a different color maybe. I have a 0, then I get a 1 here, which means I have zeros here and 1 here, right? And that means the switch is on, right? It's basically going between off and triode region, right? So that's how you kind of switch on and off this transistor strongly, I guess. So why do we need these resistors? Well, you want these resistors to be there so that the RF doesn't leak into this path, right? So it should look like open circuit to RF, but you obviously can't make those resistors very large. So let's actually discuss the trade-offs of all these resistors and devices, right? So I'll call this R1. This is R2, R2. And maybe I'll call this C2, C2. And we'll call this M switch. Okay. And this is your M inverter, maybe. Inv. All right. So first, let's discuss the role of R1. Right. So this should be large. And since R1 kind of appears, at the center node, it's immune. I mean, it's invisible to the differential signals, right? So it's kind of invisible to the tank. Um, and that's why it doesn't really matter too much. R2, however, is not invisible. R2 matters quite a bit. So we need to size it carefully, right? So for example, if R2 is large, then the phase noise drops quite significantly because it's directly connected to the tank and it's not common mode, unlike R1, right? And that's why phase noise can degrade quite a bit. But now if I decrease R2, what happens? If I decrease R2, then you're essentially kind of shorting this node and bypassing the switch, right? So then you don't have a discrete tuning anymore. So if you decrease R2, your CLSB drops, right? You don't have that discrete tuning anymore. So that's why you should design it carefully. Another thing to keep in mind is that, for example, if you're in the zeroth bit, right, where this is just C2, then R2 should be, since it's a 3-bit system, basically you want to keep the R2 C2 product constant. So when C becomes twice as large in the second stage, and we'll see when we do it in Cadence, then R should become half. And then when C becomes 4 times as large in the third stage, then R2 should become 4 times smaller, right? So you need to scale it correctly so that the RC time constant of all these switches is the same. That's another thing to keep in mind. So scale R2 such that R2 C2 is constant. Okay. So essentially that means that if this is 2 to the n, then this should be 1 over 2 to the n, right? Where n is the bit number. Yeah, I think that's correct. Okay. The next thing is, the third part is the switch transistor. So the switch transistor should be fairly large. Why is that? Two reasons. Flicker noise is lower when it's larger. And also on resistance is lower. So it's like a stronger switch basically. So the on resistance, if you remember, is kind of proportional to 1 over the W over L ratio. So on resistance is also lower, so that also reduces the phase noise, especially the phase noise figure of merit. Okay. These two things are to keep in mind. And the last one is the fourth one, which is the switch inverter. So inverter design is fairly standard, I would say. I'm not going to discuss it here. If you've done it before, then it's good, but there are some margins and all, the positive, negative margins, regeneration, inverters, all of that stuff. If you've seen before, it's good. But just to keep it simple, I'll just say that the width of the PMOS to the NMOS should be approximately 1.5. And I'll use close to minimum size. Let me just say close to minimum size. There are many considerations to keep in mind, but in this case, it's not that important because these inverters anyway kind of look like common mode to the transistor to the oscillator. Okay. I think that's pretty much it. So now we can go ahead and actually design this cap bank in Cadence. So let's do that. Okay, so this is kind of where we left off last time, just before we went back to the drawing board. So we need to make essentially a bias network. I've already done that, so I'm just going to copy it. It's a very simple network. So let's copy it and then I'll show you what it looks like. Okay, so that's what it looks like. You have your inverter there, and I've sized the width to be 1.5 micron, and the width of the NMOS to be around 1 micron. Right, and then I have 3 resistors as we drew before, the bias resistors, and then a large 1 kilo ohm resistor. This can be even larger if you like. And then this transistor I labeled as W bias and N bias, right? And we'll set these values in ADE. All right, so I also made a symbol out of this, and if you don't know how to do that, I've already covered that in previous videos, so you should go back and watch those. But if you do know, then that's fairly straightforward. Okay, so once you have the symbol, we can make a test bench, make a copy of the previous test bench, and let's do it that way. All right, so I will create some labels, label this X and Y, and we want to add our recently made bias network. Okay, that's what the symbol looks like. Our VC signal. Right now, I'm just going to the digital signal, digital control. I'll just use as a voltage source. Call this V1. And I also want to put these mask caps down here. This, what do I call this? Bank, maybe. Let's just say cap for now. Okay. That's pretty much it, I think. Oh, need to label the nodes X and Y. Okay, so let's launch ADE. Session load state. No, I don't want this state. Let me save this state. 420. Yeah. Okay, so this was the state we were using just now. So let's use that. Actually, just make 3 copies of it. I'm being a little bit lazy here and doing it as this. But now the problem becomes that I cannot change these for each of them, but you should actually scale these bias resistors for each of these bits. And so this is the first bit, second bit, third bit. So what I can do now is I can just say this is twice as large. And this is 4 times as large. Okay, that's it. So let's copy from here. And then we need to set values for these guys. Okay, so I set some values and I kind of know approximately these values because I've done this before. But as you can see, the width, the size of the bias capacitor, this is the A bias transistor. That's the one. Wait, why am I in this schematic? Yeah, this one. So if I open this, it's this one, right? I don't know why I called it bias. It's not bias, it's the switch. But anyway, so yeah, that's slightly larger transistor. Whereas, yeah, V1 is the digital signal. And the size of the mem cap, these mem caps, is 5 micron length. And then the width is around 25 micron, right? 1 micron times 25. So they're also fairly large. Okay, so let's run this and see what we get. Okay, there we go. So we have our, oh, wait a second. Change this to B2 and this to B3. Okay, so let's do this again. So when these are ones, since it's an inverter, the output would be 0, right? So when these are 1, the capacitances are off. So you should get the lowest value. That's that. And let's increase them. So we keep all of them on now. And it goes up to 600, right? So let me actually do this again. Okay, so there we go. There's a huge range. And of course, you can do it one at a time, get all the values. Something does not look right. Seems like the discrete tuning is too large. I think I made a mistake. Let me just check it again. I think I know what I did. These should not be 5 micron. These should just be 1 micron. I forgot to change it once I copied it from there. Okay, that makes more sense. All right, so let's go back here and then let's delete these, run it again. Okay, if I make this one, should be a good overlap. Yeah, so you see that there is some overlap now, right, between the two. Okay, that's good. So the delta capacitance is still around 20 femto, and if you put a vertical line, you can see this is the CLSB basically. It's around 11 femto, right? So 11 to 12. It's not exactly 15 femto as we expected, so this should be maybe a bit larger. And you can do that by increasing the size of the mask caps, so you get a higher overlap like these guys, right? But in this case, I'm just going to go with this. So let's actually look at all the bits. So this is when it's completely off. We already have that one. That's the next. Zero, zero, right? So we can check that there's always an overlap such that, yeah, you can see that this hits both of them. And then the same way here, maybe here there's a bit of a gap. Here it's fine. Here it's actually quite nice. Again, you have good amount of overlap here and so on. Okay, so these are our 8 levels. And you can see that it goes from around 120 femto to 214 femto. So that's close to 100 femtofarad range. And that's kind of what we expected. It's around 114 or so. Okay, so let's take this now into our oscillator and then yeah, see how it behaves as a VCO. Okay, so let me just quickly save this. I'll actually save this and set it up with the oscillator and we'll come back. I was actually a little bit unhappy with the fact that the overlap here did not exist. So I'm going to change this a little bit, this part. So let's actually do that. So what we can do is we can make the mask cap larger. And let's also make this mim cap a little bit larger. Let's rerun this. Okay. Delete all of these guys. And then we'll do this again. That's too much overlap. Um, okay, I need to change the size of these mim caps. Let's make the length 1 micron. Okay, that makes sense. Let's do this again. Okay, this actually makes sense. All right, so to 0. See how much overlap we have now. Why is it bad? What if I make this 50? Okay, yeah, this is what I was looking for. All right, so now you see there's a good amount of overlap, right? So I just had some numbers off, but now I think it's correct. So quite a bit of overlap. So we have our 16 femtofarad there. And if I put a vertical line, that's around 11, right? So this is our CLSB is around 11 femto and times 1.5 is around 16 femto, right? So this is perfect. All right, so now what I can do is we can plot again all the capacitances and check. So this is the 0 bit. That's the first state. Next. That's the next state. Oh, oops. I think I went too high. Did I miss? Did I miss this one? No. That's 110. Did this. Yeah, there we go. Okay, so let's see if there's any overlap that's missing. I think there should be. So you start from there, it's around 157 femto. And then you have a nice overlap there, another overlap, another overlap. Okay, this is pretty good in my opinion. All right, I think this is pretty much ready to go. One thing to keep in mind right now is that sort of the minimum value or the value of this capacitance is around, let's say the middle value is around 200 femto, right? So that's the series capacitance, which means each capacitor is already around 410 femto on each side. But when we did our original kind of calculations, we said that the capacitance that we would be needing is, if you go back here, we had already only 270, right? That's what this capacitance was. Whereas now by adding this, even when you're in the middle of the band, You already have 400 femto. So that's too high, right? So what you need to do is the easiest way to fix that is to just reduce the inductance value. We'll get to the inductor and the parasitic resistance of this tank in the next video when we talk about layouts and how to actually do layouts for the inductor, how to design the inductor. But in this case, what we'll do is we'll reduce the value of this inductance. Okay, so let's go back. And okay, I think this design is ready now. We can put it into the oscillator and see what happens. So let me actually do that now. Okay, so let's use this one where I still had a voltage source out here, and later we removed that voltage source, if you remember. But just for the sake of simplicity, I'm going to not use that design and just use the design that had the voltage source. Okay, so what we can do now is make a copy of all of this, bring it out here, and then also copy of this, and I can place it anywhere. So let's relabel these things. Right, and we can delete this capacitance and this capacitance. Don't need that anymore. Okay, the reason is that I said that this parasitic capacitance, when everything is off, not parasitic, but the capacitance when all the states are off, even that is too high, right? So we'll deal with that. Okay. And actually, let's just keep it full screen. So we have a state that we used earlier. We'll just continue with that because that has all the parameters already loaded up. Yeah, the phase noise form was around -180, but that was at 100 kilohertz offset. Let's make it 1 megahertz. And then we also want to include all the other new variables which we added in, right? So I don't remember these values. Let me actually quickly fill them in from what we just designed, which is this one. Okay, cap min 55, width is 1 micron, and bias is 18, our bias 1K. Let's just set this to 111, 545 milli, T, bar mim is 5 microns, variant max is 100, and the width is 2 microns. The bias is okay. All right, so let's run this and see what happens. Putting this to the side. All right, so you can see the form dropped, right? Swing also dropped, both voltage and current. And that's because the Q of this tank now is much lower, because earlier we had an ideal kind of capacitance, whereas now these capacitances all have some loss, right? So since the Q dropped, and there is a way to look at what the event, if you have a capacitance with some Q, how much does it DQ the actual tank? But I don't really think there's any point in doing that analytically. All you need to do is that you need to drive this oscillator harder, right? So that it can actually fully switch the current to both sides. So we increase the number of fingers essentially to increase the GM, right? Because you need to increase the negative capacitance. Okay, so that's a little bit better. You can see the form has improved to around -178. And you're switching the current pretty well because the maximum current is now 1 milliamp or so, right? Which is what we expect. Problem, however, is that the PSS free, we can actually turn off HB. We don't need that. Is around 8.9 gigahertz. This should be around, so right now everything is off, right? So when everything is off, it should be very high. Actually, it should be around 11, whereas it's around 9 gigahertz. And that's because I told you that the capacitance is much larger, right? Because of the capacitances of the varactor now. So to compensate that, we will reduce this to around maybe 680 pico. Let's run it again and see what happens. Okay, it's around 10.27 or so. So let me actually tune these values a little bit more to get the band that we're looking for, but essentially the design is done. It's just about tuning these, so I'll tune these and come back. Okay, that was pretty quick. All I had to do was change the inductance, make it a little bit lower, so it's around 590 now, and the number of fingers to 40, right? So now we can check what the maximum value of frequency should be. So all the varactors should be, all the caps should be off. So that's 111. And we want this one to be 330 milli. Right? That was the least capacitance. So let's see what we get. Okay, so we get around minus 181. That's actually a pretty decent form, I would say. And you can see that at 1 megahertz offset, it's around minus 100 dBc per hertz. And we have slightly higher frequency than what our upper band was. It's around 11.17. So then we can turn on all of them and see what happens. So this is around 800 milli. Let's run this. Okay, so you can see it's less than 9 gigahertz, so it's covering the whole band from 9 to 11. The form drops a little bit because when the switches are on, there is an on resistance, and that on resistance can reduce the phase noise. Also, the swing drops a little bit, but you still have large current, right? So that pretty much completes, I would say, the design of the oscillator. I don't want to go into too much detail in this video. This is just sort of a first pass design of a VCO that has both continuous and discrete tuning. Of course, you can do a lot more from here. So let me actually just quickly save this. Right, so you can investigate, for example, we looked at that in the previous video, which was in the tail current effects video, which transistors were contributing more to the phase noise, and then try to see if we can minimize those. There are many techniques for phase noise reduction of oscillators, so that probably requires a separate video. The next thing that I want to do is I want to replace these with a real inductor that will simulate in HFSS using a full wave EM simulation. We also need to look at the load pull. So for example, right now there is no load for this oscillator, right? It's kind of not connected to anything, but in reality, it will be connected to the next stage. So in order to do load pull, we will first do the layout and then we'll do the load pull. So we'll complete the inductor, add the inductor model to this, and then we'll do a layout of this whole oscillator. And once we're done with the layout, then we'll do load pull and see what's the ideal load, right? So once you have the ideal load to maximize, let's say, output power, then you can kind of design interstage matching to the next stage. So following this, I'll discuss maybe frequency doubler design. That's probably the next stage that will come into this chain. Moving forward, I might not use this discrete tuning. I'll just stick to continuous tuning, just to keep it simple. Discrete tuning we might revisit when we do digital PLLs sort of in the far future. As of now, sort of this is probably enough because this gives us probably enough bandwidth for the automotive band at least. Okay, so hopefully you're excited about all those videos to come. If you have any questions or if you have any comments, if you found any mistakes that I made, and if you have any suggestions on how this design can be improved, if you have any insights, I'm really happy to hear about them in the comments. So please leave them below. If not, I'll see you in the next one. Thank you.